time-based real-time GC is a sort of a separate garbage collection thread that executes in some sort of periodic schedule. And there are two main types. There's the metronome collector, which comes from IBM Research Labs, and the Lund collector, which comes from the University of Lund in Sweden. And they take exactly the opposite approaches to doing this. It's kind of an interesting little interesting part of the real-time GC world. So metronome runs at the highest priority of every thread in the system. The Lund collector runs at the lowest priority of the time-critical threads. And we'll define time-critical threads in a little bit. So metronome, it spreads the GC across all periods sort of evenly, but it has the lowest maximum latency. The Lund collector has the lowest maximum latency of the two. And the Lund collector, very, very, very crucial point. The analysis that you have to do to get the collector to work right only has to be accomplished for those time-critical threads. For the metronome collector, you have to analyze the whole system. And there's some cons about this as well. We can talk offline. My marketing guy is spinning his fingers over there telling me to speed up. Metronome works like this. It's pretty obvious. You sort of set it up so that it has a cost and a period. It's a periodic process. And because it has the highest priority, it takes the first whatever time units from each of its period. So whatever that time unit is, that's your lowest maximum latency. 1 millisecond, 2 milliseconds, they're sort of in that area. So they're always going to be interrupting all of the tasks at the first millisecond or first 2 milliseconds of each of the periods of the GC. The Lund collector, or Hendrickson's GC, is that because it's the lowest priority of the time-critical threads, the time-critical threads actually interrupt the garbage collector. Now, there has to be a little critical section there, of course, but that's the interesting point. And here's how that works. So we have 3 threads, 2 time-critical threads, and the RTGC. And the 3 periodic threads form a periodic system of 3 tasks, which is feasible. And those are the cost and periods in some time units, 5 out of 29, 12 out of 50, and 50 out of 163 for the GC. And there's the execution pattern for a few of the periods. You can see, of course, the highest priority. I did this sort of rate monotonic assigning priorities here in the rate monotonic way. So the highest priority is the thread with the smallest period. It gets the first few time units, the first 5 time units of each of its periods. The second thread will get what's left over, and sometimes it gets preempted by the higher priority thread, which makes sense. But look at the real-time GC. It doesn't get any cycles in each of its periods until the other guys are done doing what they've got. So the 2 higher priority threads preempt the GC. And that's why we're able to get down in the below 200 microsecond latencies with the Hendrickson approach. Of course, the non-time critical threads get what's left over. Okay, in Java RTS 2.0, we started with the Hendrickson approach, and we made a little modifications to it to make it a little bit easier to configure and not so reliant on doing an actual feasibility analysis. We have some minimal policies in there now, but we're thinking about the way we've structured this is it might be interesting to have the GC execute some heuristics to actually get itself into a situation where it's really kind of understanding what the application's doing and then setting its own parameters as time goes on. This is how it looks in Java RTS 2.0. Of course, the NHRTs are above everything, and they execute whenever they damn well please. The real-time threads now are split into two chunks. So you can have real-time threads with higher priority than the GC and real-time threads with lower priority than the GC. And then non-real-time threads always have lower priority than the priority of the GC. And the GC there has a range of priorities. It starts off at its initial priority and then moves up as it needs to do more work in our model today. This is how it looks. This is a fully parallel, concurrent garbage collector, so multiple instances of it can run on CPUs if it's available. And you can see in the one CPU case here, the garbage collector kind of realizes the memory's getting low, so it boosts its own priority and takes some time from the non-time critical threads. Always the time critical threads are always going to preempt it, though. On a 2 CPU system, notice that the critical NHRT and the RTGC are executing at the same time on different CPUs. And so the GC can get done a little bit earlier. So we have critical threads. What we want to do is there's actually a whole slew of command line parameters you can use to set up the real-time GC, but there's 2 primary ones. Min free bytes is really the big one. And think of it this way. Is kind of imagine a heap. And you have this high water mark that you can move from the top of the heap down. That's the minimum critical reserved bytes. Everything above the high water mark is reserved for the time critical threads. None of the non-time critical threads can allocate memory above the high water mark. And so that high water mark forms a buffer of sorts, and that the time critical threads can allocate from that while the GC is actually deallocating from that upper area of the heap. And they can kind of flip-flop over time, and as long as the collector is getting enough CPU cycles, it will clean up enough of that upper area so that the time-critical threads never experience an out-of-memory condition. There's always appears to be free memory there for them. And I've done this with customers now in the financial space. We go in, we take their code, we put it in real-time threads, which, by the way, have exactly the same characteristics of Java-lang threads. So you can do a one-for-one replacement from Java-lang thread to real-time thread. And so we put their code in real-time threads, and we start moving that critical minimum reserve bytes, or that high watermark, down the heap, and we keep taking tests of their response times. And eventually we get to the point where we have enough money and the response times all flatten out where they don't get any blips anymore. And so it's a very, very simple but yet empirical thing to do to get a system to behave well. And there's also some settings for the non-critical threads, the number of GC threads you can control on the command line and so forth. So in our 2.0 product, on a particular machine, a 4-way Sunfire 4100 with Solaris 10, it's an x86-based machine, we've got these numbers running our little in-house tests. And that's pretty good. You think about an order of magnitude better max latencies for no-heap threads over real-time threads. But 130, 200 microseconds is pretty good. If you don't have a lot of work to do, you can get a 1,000 hertz process pretty easily into that. All right, so the demo. Yeah, why don't you fire that up and